So today we'll start with next case of influence line diagrams. Let us note down the problem. Now we'll solve for UDL, uniformly distributed load, where span of the load is less than span of the girder. A UDL of span 15 kilonewtons per meter and length 4 meter crosses the girder of span 12 meters from left to right. Determine reactions, shear force and bending moment at section 5 meters from A, and absolute maximum bending moment. Absolute maximum bending moment means load placed at the center. Say this is the girder AB, length 12. So I want at x is equal to 5. So this is L minus x is equal to 7. Now here the UDL is crossing the girder from left to right. Say this is the UDL and its load is 15 kilonewtons per meter and its span, it crosses from left to right in this direction, and its span is 4 meters, span of this load. So for this I have to do the analysis. So step 1, reactions. For this, first for the reactions, let us draw a standard diagram. So this is the standard diagram for shear force. Now place the UDL here, 4 meters. Mark the ordinate. Let this ordinate be 1, y1. For standard shear force diagram for reactions, this ordinate is 1. Now I need to calculate area under the load. For that, let us calculate first y1. So 1 divided by 12. Now this span is 4 meters. Overall is 12, this is 4. So this remaining is 8. So let us write down the values. 1 divided by 12 is equal to y1 divided by 8. 1 divided by 12 is equal to y1 divided by 8, or y1 is equal to 0.667. Now RA and RB, they will be same. RA and RB is equal to load into area of diagram below UDL. So always for UDL you have to calculate the area. So load is 15 kilonewtons per meter. Area of this trapezoid. Area of this trapezoid is given by 1 plus y1 divided by 2 into this span 4. Average height 1 plus 0.667 divided by 2 into 4 span. So that gives me the value 50 kilonewtons. So RA is equal to RB is equal to 50 kilonewtons. Next step, step 2. Shear force at section x is equal to 5 from point A. I have to calculate shear force at section x is equal to 5 from A. Now first let us draw the standard diagram. So this is the standard diagram for shear force. X is equal to 5 meters from A, L minus x is 7. So this ordinate is given by x by L. So that gives me the value 0.417. This ordinate is given by L minus x by L. These are the standard values. So this gives me the value 0.583. Now I have to place the load once towards the right, towards the left. Towards the right, place it like this. So this dimension is 4 overall is 7, this is 4, it means this is 3. Next step, place the UDL on the left side. So this dimension is 4. So let me project it here. So this dimension is 4, this is 1. Now I have to find out area. For this, project this line. Let this dimension be y2 and this ordinate be y1. So I have to find these areas. Area under the load. So to find out area under the load, I need to calculate y1 and y2. Now to calculate y1, I know this ordinate 0.417 divided by 5 is equal to y1 divided by 1. So 0.417 divided by 5 is equal to y1 divided by 1. So or I get the value y1 is equal to 0.0834. So similarly here, this value is 0.583. 0.583 divided by 7 is equal to y2 divided by this dimension, that is 3. 0.583 divided by 7 is equal to y2 divided by 3, or I get the value y2 is equal to 0.25. Now this value, this area into load is negative shear force and this is positive shear force. Maximum or negative shear force is equal to load into area of diagram below UDL. So load is 15, area, average height, that is 0.417 plus 0.0834 divided by 2 into span of UDL 4. This value, this ordinate 0.417 plus y1, that is 0.083, average of this into this span. So this gives me the value minus, or I can get plus reserve, 15.01 kilonewtons. So similarly, positive shear force is equal to load into area of diagram below UDL. So load is 15, average area here 0.583 plus y2 divided by 2. So this gives 0.583 plus y2 value is 0.25 divided by 2 into span 4, span of the UDL, into 15. So this gives me the value 24.99 kilonewton. This is positive shear force, this is negative shear force. Now arrangement of UDL. For maximum bending moment, the arrangement of UDL should be such that section X, this is my section X at X is equal to 5, should divide the load and span, here span means span of the girder, in the same ratio. So I have to put the UDL in such a way that 5 by 7, this should be equal to, let this be A, this is 4 minus A, 4 minus A because this span is 4. So this ratio should be same. So 5 divided by 7 is equal to A divided by 4 minus A. 5 divided by 7 is equal to A divided by 4 minus A, or 7A is equal to 5 into 4 minus A is equal to 20 minus 5A, or A is equal to 1.67 meters. So you have to place the load such that 1.767 on this side, rest on this side. So once you have placed the loads, I have to find out this ordinate, this ordinate, this ordinate. So this dimension is given. This is 1.67. This is 4 minus 1.67, that is 2.33. Now this overall from here to here, this is 5. 5 minus 1.67, 3.33. 2.33. From here till here, this is 7. 7 minus 2.33, you have 4.67. This value is x is equal to 5, L minus x is equal to 7. Now I have to find area of this and this separately. Let this ordinate be y1, this ordinate be y2. This for bending moment, this value is given by x L minus x by L. So that gives me value 2.92. Now let me solve for this. I'll solve for y1 and y2. So 2.92 divided by 5 is equal to y1 divided by 3.33. So 2.92 divided by 5 is equal to y1 divided by 3.33. So y1 is equal to 1.94. So similarly, 2.92 divided by 7. 2.92 divided by 7 is equal to y2 divided by 4.67 is equal to y2 divided by 4.67, or y2 is equal to 1.94. Now maximum bending moment is equal to load into area below UDL. So load is 15. Now area, here I have to find this area separately and this area separately, and this is given by 2.92 plus y1, 1.94 divided by 2 into span. This span is 1.67 plus average height. So 2.92 plus y2 divided by 2 into 2.33. 2.92 plus 1.94 divided by 2 into 2.33. So solving this, you get the value 147.8 kilonewton meters. So this is maximum bending moment at the required section. Next step to calculate is absolute maximum bending moment. Absolute means occurring anywhere on this section. So this bending moment I had calculated at x is equal to 5. Now I have to calculate absolute maximum bending moment. Absolute maximum bending moment occurs at mid-span with half the UDL on each side. So I have to calculate at mid-span. X is equal to 6, L minus x is equal to 6. So place the loads half on each sides. Overall span of the load is 4 meters. So 2 and 2. Now this ordinate is given by x L minus x by L. So x is 6, L minus x is 6. So you have the value 3. So similarly, project these. Let this ordinate be y1, this ordinate be y2. Now I have to find areas of this and this, two trapezoids. Mark the distances. This overall is 6. From here to here this is 2. So this remaining is 4. First find y1 and y2. y1 divided by 4 is equal to 3 divided by 6, or y1 is equal to 2. Similarly, y2 is equal to 2. Now, absolute maximum bending moment, same equation, is given by load into area of diagram below the load. So, load is 15. Area of diagram, once this diagram, another this diagram. This is 3 and this is 2. Average height. 3 plus 2 divided by 2 into span. This span is 2. This area and this area is same. So multiply by 2. So you have the answer 150 kilonewtons. This is absolute maximum bending moment. This completes the problem. Thank you.